Well, I want to start by talking about singular values. And they're not eigenvalues. So I want to talk about what are they and make sure we're somewhat on board with them. And then we're going to do an application that uses them. Okay, so we have singular values, and maybe we should say versus our eigenvalues, just so we can say which values reign supreme. All right. So, well, let's talk about eigenvalues first, because we're more familiar with eigenvalues. So this is a case where oftentimes we think about it as ax equals lambda x, where x is non-zero. And geometrically, how do we think about an eigenvalue? So what's the geometrical intuition? What does it mean to be an eigenvalue geometrically?
It stretches things. I want it to be the amount stretch in a particular direction.
Right. So the thing is, when you think about A, it's a map from the space back to itself. Now this is important. This is one of the things that's going to distinguish singular values versus eigenvalues. And what happens is that if I'm an eigenvalue, that what will happen is after I apply A, so here is x, I'm going to stretch. Now I might possibly also reverse direction depending upon the value of lambda. If lambda is complex, well, that makes it a little bit more complex to see, but we'll ignore that for now. But just basically the punchline is it's a scaling direction. And so, all right, so that's cool. Now, what about singular values? What's happening there? Are they the same as eigenvalues, or are they different? All right, good news, they are different. All right, so you've mastered that. And now, the thing about singular values is you don't have to map from a space to itself. So in other words, when we talk about eigenvalues, you always have to work with square matrices. For singular values, you don't. Now, what's the underlying geometrical idea? So this is the one I've been told, and so I don't know if this is the same as yours, so I'm just going to tell you the one I've been told. And you can say, yes, that's what I knew all along. And so again, I'll just say that we have our map B, and it's not going to be as simple as like, oh, bx equals lambda. Okay, it's not that, but let me mark what's going to happen here. You start with your sphere in your base state. So in other words, before you map, and now what's going to happen? So in our case, if I'm going from, say, a two-dimensional space to a three-dimensional space, my sphere is a disk. What will a disk map to under a linear transformation?
An ellipse.
It'll map to an ellipse. Very good. Now, it could even map to something that's, like where you collapse it down to a line, but it's going to be some form of ellipse. And so it's going to map into a two-dimensional version of this thing. All right, so that's where we have, it's still a linear transformation, so we're still staying linear. All right, now, here's the question for you. In terms of this picture, I haven't yet justified what singular values are. I've just said, if I have a sphere, it maps to some version of that sphere. But that's been stretched and whatnot. Okay, so the key thing is when you have an ellipse, we'll test your knowledge of ellipses, what do you have? Now when you have a circle, what do you have? You have a radius, yes.
And it has an A in it.
It has like an A and a B, like a major and a minor, right? And so what turns out to be being captured is you're looking at these lengths. And so you have S1 and S2 are the lengths of your two, major and minor one for an ellipse. And here, well, I said a disk, we'll make it a unit disk. And so our singular values for this mapping would be S1, S2, and I can't remember if they throw in 0. Well, if needed, you throw in zeros. You pad it to be whatever you need it to be. That's a good rule of thumb, right? You just make it work. And so that's the geometrical underlying thing. And so there's a couple of things to know. So singular values work with any matrices. Doesn't have to be square. And so that makes it a little bit more general. And so if you have any matrix which isn't square, you're like, I wish I had eigenvalues. You say, well, hey, wouldn't you know? You can use singular values. I'm like, what? I can use singular values? That's awesome. Okay, so they work for any matrix, including non-square. And another thing to note is that your singular values are real numbers. In fact, they're non-negative because we have this geometrical interpretation. Okay. All right, so that's a nice thing. It means that, okay, we can do it for a broader class of matrices. We don't ever have to worry about things being complex. This is like a win-win. Wonderful. All right. Now, is there a relationship between singular values and eigenvalues? So suppose I take A, and let's suppose we make A nice. And in other words, something that we've been using for our class, let's make it real symmetric. What can we say is the relationship between singular values versus eigenvalues?
The eigenvalues are the square roots of the singular values. It might be the other way.
Well, it's not quite that.
The absolute value.
It's the absolute value.
Yeah.
That's pretty
But I don't think you need the square root.
Okay.
You just need the absolute values.
Okay.
Because you're taking the square root of the eigenvalues of A star A.
Yeah.
And so your eigenvalues square. And so when you have real symmetric, then the singular values are just the absolute values. Absolute value lambda 1, absolute value lambda 2, all the way down absolute value lambda n.
When you wrote on the top left,
Mm-hmm.
when you wrote singular matrices, do you mean singular values there? Below.
Oh, yeah, you're right. I should have said singular values. Thank you for pointing that out. Good. All right. We can even see this in terms of our original idea here. Because if we are nice, we have real symmetric, what's true about our eigenvectors? They're orthogonal. And so what we can do is we can have our sphere, we start with our sphere on the inside, and we choose our original sets of our orthogonal directions, our radii, if you will. We just pick them to be the directions of the eigenvectors. Now when we apply the map, what will happen is we just stretch in those directions. And so the scaling factors are, in fact, the singular values in terms of the map. So geometrically, it can also be seen that this is what's going on. All right. Well, what's the point? Well, we're talking about spectral graph theory. And almost always you say, aha, spectral graph theory is you look at eigenvalues and you say, what can you learn about a graph? Looking at the eigenvalues. But sometimes, results are actually singular value results. And so I want to talk about one such result today. So that's my goal for today. And, excuse me. So here is a fact. And this is a linear algebra fact, and so we're just going to inherit it. It's about singular values of matrices. And it says the following. If I look at X transposed my, then that's less than or equal to sigma m times norm of X, norm of Y. Now, I'm going to be careful here and make sure we understand what all these pieces are. So, sigma m, this is the largest singular value. Excuse me, I have a frog in my throat. Okay, all right. So, hopefully that clears that out. Over here on the left-hand side, these bars mean absolute value. Because when you look at X transposed my, we really interpret that as a number, and so we're just saying just take the absolute value of that number. So the absolute value of that number is less than or equal to the largest singular value. And now, here, these aren't quite absolute values. What are they? Well, these are the two norms of vectors. So the L2 norms. Okay. So, with that in place, we're going to talk about an idea. So there's this notion called discrepancy. And I'll write down a formal definition. And so the discrepancy of a graph, it's a way to measure your graph, is the smallest alpha so that for any x, y subset of the vertices, and I'm going to pause here and I'm going to cheat by making a small change, which we're going to undo later. I'm going to put in D regular graph. So you know you're cheating when you make things regular, but I want to go historically. So we're going by historical. So it was first talked about for regular graphs. For any x, y, we have the number of edges between x and y minus d over n, size of x, size of y, is less than or equal to alpha square root size of x, size of y. All right, so there's a lot to parse here. Probably the first thing is why? Why do we care about this? And then after why, then you start to say, wait, but why? And where are these terms coming from? So let me talk about the intuition about what's going on here. So we have our sets x and y subset of vertices. So we are going to think of our graph G, and here's our graph G. And we'll think of x and y. Now, I'm not making any assumptions at all about x and y being disjoint. So x and y are arbitrary. They could even be the same. But for now, we'll just say x and y are just subsets of the vertices. All right, so here's x, and here's y. So at EXY, do you remember what this is? Yeah, so it's the sum over all little x and x, sum little y and y. I'm debating about how to write this notation. Well, x, y, and edge. So this will be an indicator. So sometimes you'll see this square bracket notation. I think this just shows up in concrete math, which is a book. It's a good book. It's still in print. And it's not about making cement. So the square bracket's either 1 if it's an edge, 0 if it's not an edge. So you're counting the number of edges. So this is the number of edges between x and y. And you just have to be careful with overlap. And so if you do have overlap, what happens to your count? In the overlap, you count twice. Yeah, that's it. All right, so we have some quantity here. So this EXY, this is saying the number of actual edges between x and y. Okay, so that's what that's counting. Now we come to the second term, this d over n, size x, size of y. Well, what would that count? Just, what do you think it should count?
I feel like degree over total number of vertices? I don't.
Well, think about it from the perspective of a single vertex. Or maybe come back here to x, y is an edge. What's the probability that a certain vertex is an edge? What?
Sorry, are you
What?
saying?
A certain edge is an edge.
Okay, yes.
A certain pair. What's the probability that between x and y I have an edge? Maybe that's the better way to say it. Think about fixing x. So fix x. What's the probability that going from x to y you have an edge?
X to big Y.
Degree of x divided by negative y. Divided by n minus.
Sorry, are you saying between two specific edges?
Well, think of vertex x as I have vertex x in x, I have vertex y in y. How likely is it that that's connected? So put on your probability hats and imagine that the edges were quote unquote random.
Total number of edges
It's just,
divided
yeah, it's, I just say it's the degree of that vertex divided by the total number of vertices.
Right, the degree of the vertex divided by the number of vertices. So the probability of any particular edge, if I were to think of things as being random, would be any edge would show up with d over n. And now, well, if I do it over all possible pairs, what the second term is, this is the number of expected edges between x and y if everything's random. Or let's say super random, purely random. So I have the actual number of edges that are present, and I'm saying, well, compare it to the expected number of edges which are present. So in this case, what does discrepancy try to capture? Kind of like an error.
Like variance sort of thing?
And
No.
so one way I like to say is discrepancy is asking the question, how random are my edges? So a small discrepancy, well, that would tend to say that these numbers are very close. A large discrepancy would say there's something which causes it to be very far. So a large discrepancy says somewhere in the graph there's big pieces where the difference between the actual number of edges versus what you should expect is a very large thing. So it's very non-random. So it's a measure of randomness. Now, why do we include the size of x, size of y? Well, essentially what we want to do is sort of temper it. We want it to be more tolerant. of large sets versus small sets. And so this is just makes it work and it makes the proof very slick. All right.
Alpha is just any real number.
Right, but the goal is to find the smallest alpha.
Yeah, so
Yeah.
I was just making sure.
But of course not, you can't pick alpha to be 0, for instance. But, alpha is 1,000,000. Yeah, sure, you could pick alpha to be 1,000,000, but it's probably not a good alpha. Now, I suppose if your degree is high enough, 1,000,000 would actually be a bad choice.
What does this look like on a small graph?
On a small graph?
Could we do this on a cycle graph?
In theory, one could do this, but the thing is, it's if you think about what's happening, we're going over every possible subset X and Y.
Oh.
Right? And so there's a lot of those. So if you have an n-vertex graph, there's 2 to the n subsets that can go in X, there's 2 to the n subsets that can go into Y. So it would take you a very long time to exhaustively actually find the best alpha. So this is not an easy parameter to compute if you get large.
Can't use
Oh yeah, okay, so we're going to talk about that. Because right now you're like, this has nothing to do. Why did you talk about singular values? Yes.
Do we have any sort of hold on what alpha can appear as the discrepancy of some graph? Like, probably not any irrational numbers, but can you get what kind of positive rational numbers can
You probably can get fairly close. For most graphs, we'll talk about why I'm bringing this up. And we'll see that there is a connection to singular values. So there is a punchline coming here. All right. Are we ready?
Guys, sorry.
Oh, no, we're not ready. Okay.
So to be clear, we usually when we pick real numbers, we say infimum. The infimum in this case is a minimum, right? Also.
Yeah,
And
because it's a finite problem.
are we going to change it from being d-regular to any graph?
We will,
Okay.
but we have to make it more complicated.
I see.
So the question is, how do you change this D? And we have ways of changing that. We will make it work. All right. Okay. So, result. And I believe this is, you'll sometimes see this as expander mixing. And due to Alon and Chung. And it says the following. Alpha is less than or equal to sigma 2 of A. Now, usually it's not written this way. It's not written in terms of the sigma sub 2 and being the, so sigma 2 is shorthand for the second largest singular value. So we talked about sigma, that's the largest singular value, and so sigma 2 of A. Now, if you remember, for D regular, what's true about our eigenvalues for an adjacency matrix?
They're all perpendicular to the elements vector.
Well, that's eigenvectors, but eigenvalues, what do we know? D is one of them, yes. So we have D, we'll call that lambda 1, and then we have everything else. Well, they may be less if our graph is connected, but for right now, we won't make any assumptions about connectivity. And but on a side note, if our graph is not connected, stepping back here, what's true about discrepancy for a graph which is not connected? No, it works. It's perfectly true, but what happens? You're going to get
Highly non-zero.
you'll get 0 between your two components, and then you have this part which tends to be large. And so what will end up happening is you'll get a fairly large discrepancy. And so another way of saying it, it's not very random to be disconnected. All right. So when we oftentimes, instead of writing this as sigma 2 of A, this is written as alpha less than or equal to the min of absolute value of lambda I, where I goes from 2 up to n. And then people are like, ooh, so it's an eigenvalue result. No, it's a singular value result. It just happens that singular values have this tie to eigenvalues. So it's hiding what it really is deep down. Okay.
Wait, why is it minimum when you said it's the second largest?
Right. So you're right. It should be the max.
Okay.
Thank you for pointing that out. So the max. And so oftentimes the way this is phrased when they talk about expander mixing is you have one eigenvalue of d, and what you'd like to have all your other eigenvalues be small. So if all your other eigenvalues are small, that makes sigma 2 small, which makes your discrepancy small. All right. So let's see. I think we have time for a proof. We should. Every class should include a proof of some sort. All right. So what's our proof? So here we go. Proof. I'm going to look at the following matrix. A subtract d over n j. I'm going to look at this matrix for a few minutes. And I'm going to think about what's happened here. Now, we know what A is. What's this doing? Subtracting d over n times j. I could rewrite this as A minus d, and this will get me into trouble trying to do this in real time, but okay, 1 over root n, all one's vector, times 1 over root n, all one's vector transpose. That's another way to write this. Okay, so what's the effect here? What's going on with this matrix? And in particular, compared to the eigenvalues for A, what are the eigenvalues for this matrix M? And if you want, we can ask a different question that's very leading.
Well, so one of your eigenvectors is the all ones vector. Everything else is perpendicular. True. A b, you get lambda v, and then you multiply that, you get 0.
Okay.
So you get the eigenvalues of A, except for D, and then D is now...
So the eigenvalues of M will be 0, lambda 2, up to lambda n. So essentially what you can think of, there's this notion of what's called the projection. And so this matrix here, 1 over n times j, that's the projection onto the all ones. And so when you do this subtraction, ultimately what you're doing is you're basically saying, for the eigenspace associated with the all ones, we're going to do a modification. And we just happen to be in a very nice situation where we say, well, we know what the all ones looks like. And from there, we say, all right, so given that we know what the all ones looks like, what happens to that eigenspace? Well, it was originally associated with the eigenvalue d. Now it's with d minus d, which is 0. Okay. So, how does sigma of m compare to sigma of a? Well, this is where we want to be a little bit careful. My claim is sigma of m is sigma 2 of a. Why is this? Well, we still have real symmetric matrix, so we're still looking at the absolute value of the eigenvalues. And what's true about our eigenvalue of D for the matrix A? Since our graph is D regular, D is the largest. So essentially we took our largest and said, move it to 0. And so we say, okay, so now I have to take the largest of what's left. So that would be the second largest. So that's why there's a sigma 2 of A. And now you're like, things are coming together. Okay. So, next up, I want to talk about two subsets. So let x and y be subsets of your vertices. And we're going to make vectors. So what's an easy way to turn a subset of vertices into a vector?
Set them all equal to 1,
So okay, say that again. You're on the right track.
I'm understanding what you're saying.
Oh, no.
Set them all equal to 1 and the rest equal to 0.
Okay, set all what equal to 1? You're on the right track.
Label all of the vertices
Right?
in a way than just ones as a characteristic.
Right. So you use the word character. I would probably use the word indicator, but you have the right idea, right? So we're thinking of, we're going to make a vector, which is an indicator vector. So x is associated with a 0, 1 vector, which is 0 if you're not an x, and 1 if you are an x. And now we'll do the same thing for y. Y is, again, a vector y is all 1 y. That says, hey, we're 0 if we're in the set y. We're 0 if we're not in the set y, 1 if we are in the set y. Okay, well, this might be looking really familiar. And now we're going to ask, what is x transpose my? And we're going to say that's less than or equal to sigma of m, size of the vector x, size of the vector y. And this came from our fact about singular values of matrices. And so we're just going to start chipping away. All right, pick a term. The right-hand side probably is a little bit easier. What do we know about sigma of m? Yeah, that's easier because it's on the board. It follows the classic, if a professor asks a question, 0, 1 are somewhere on the board. Okay, sigma 2 of a. Now this one's not quite on the board, but it's almost, you can reason it out.
Is square root of size of x times the square root of size of y.
Right. So when you think about the norm of this x vector, well, it's 0 if you're in x, 0 if you're not in x, 1 if you are in x. I'll get that right sometime. And so when you take the 2 norm, well, it turns out it's just how many things are in x. And then you have to take the square root, so you get the square root size of the set x and the square root size of the set y. And you're like, whoa, this is looking really familiar. All right, so that just leaves us with what's happening on that left-hand side. But you already have a feeling like, I know where this proof is going. All right, so here we go. Left-hand side. We have our indicator function x. We're going to take our a minus, and we'll do d over n j. And then we have our indicator function y. Well, we can just distribute. This becomes indicator function x, a indicator function y. And then d over n is a constant. And then we have indicator function x, j, indicator function y. All right. So, what's being counted here? Well, if you think about it, whenever you multiply on the left and right by an indicator function, what does it really amount to? Picture-wise, you can think of it as doing the following. You have your matrix A, and then you say, okay, there's a set X, and then there's a set Y. And what you do is you look at the submatrix and you add up. So it's adding up everything that's in the box. That's what happens when you multiply on the left and right. So when you do that, what does the first term give you?
Number of edges between x and y.
It's the number of edges between x and y. So this is the number of edges between x and y. All right, minus d over n. Now here when you do it, it's a similar box, but now your box is full of just ones. So it's the size of x times the size of y. So minus d of n and size of x, size of y. And we're done. Because we wanted to show, we wanted to find the smallest value that we could put here. And we said, you can put sigma 2 of a there. And so that says that our discrepancy is bounded by sigma 2 of a. And life is good. All right. Now, a couple of comments. So, if your eigenvalues, except for the d eigenvalue, are all close to 0, your discrepancy is small. Is the opposite true? Which is to say, if your discrepancy is small, must it be the case that your eigenvalues are close to 0? And the answer is yes. Now that's a little bit harder proof. And that's why I'm not going to prove it. But I'm going to wave my hands, and I'm going to talk about why it's true. So there's something along the lines of, this is hand waving, so I'm not claiming that this is exactly right. But sigma 2 of a is less than or equal to some constant times, let's see, it looks like, well, some constant alpha times some constant d plus log of alpha. Something like that. I'm going to wave my hands. Just say that that's true. Now, you might say, this makes me nervous because I see a log of alpha, and if alpha is small, log of alpha tends to be large, but alpha log alpha goes to 0 as alpha goes to 0. All right, so if alpha is small, then that says sigma 2 is small. All right, so how do you argue this? Because this does not seem plausible that we can make such an argument. So what can we do? Well, what we have is that we have, okay. I'm trying to find the right way to say this without having to correct myself 5 times. Maybe I'll only have to correct myself 2 or 3 times. We want to say something about x transpose my. That's our goal. So we know, the basic idea is we know we have a small alpha. So x transpose my is less than or equal to alpha size x size y. And this is for, well, sorry, I should do little x, little y. But this holds for any x and y which look very particular. In other words, they look like 1x and 1y. So we know automatically that this is true. Okay. So now we say, but wait, most vectors don't look like that. And it's true, most vectors don't look like that. But here's the great aha, which is to say, even though most vectors don't look like that, most vectors do look like a sum over few, called x sub I, 1, x sub I, and c sub I. So what you can do is you can approximate any vector by, in some sense, discretizing it. So think about taking your entries of your vector and chopping them up into finite number of bins. And you have to be careful how you do this. So there's a lot of hand waving going on here. If I haven't said it yet, I'm hand waving here. And so you can discretize your vector. And then after you've discretized it, you say, well, look, I can pull it apart so it looks like some constant times an indicator vector. And I can do it in such a way that there's very few of them. So that depends on how I go about discretizing. And that allows me, now the few is what gives you your C's and your D's. And also your log alpha comes into play. And that just because of how, again, hand waving. There's a paper on that. So that's why you, in some sense, get an equivalence. So the punchline is there's this equivalence going on, which is to say sigma 2 of A small if and only if discrepancy is small. So our eigenvalues are close to 0 if and only if our discrepancy is close to 0. So we said discrepancy is capturing randomness. And small discrepancy is our edges are random-like. So now we can say, oh, we can capture how random our edges are by looking at our sigma 2 of A. How small our eigenvalues are give us a notion of how random our edges are. And so that's an example of something called quasi-random. But looking at the time, maybe we'll talk about quasi-random at the start of next time, because I feel like I should do it proper justice and not just rush through it. And talk about things such as how quasi-random inspired a license plate for an RV owned by Fan Chung and Ron Graham. You know, because they believed in mathematical license plates. So their RV had the license plate Q random for quasi-random. And then Ron's car had, his license plate was number. And he always dreamed of having an interaction with the police officer, being pulled over and saying, all right, what's your license plate number? And to which he would say, number? Stop being a wise guy. What's your license plate number? Number? But, you know, that interaction never happened. But, you know, there's always the dream, right? And, of course, Fan Chung, my PhD advisor, her license plate was theorem. Now, what you might not know is I have a car. And I know, it's crazy. Even though I ride the bus, I actually own a car. And it has a license plate. And so my license plate is lemma.
Great.
And so, because their cars were SUVs. And I thought, okay, a theorem is big and powerful. But my car, it's a Toyota Prius. And so I said, okay, this is a demonstration. Theorems are big and powerful, but lemmas get better mileage.